Hello and welcome to another video in this series, taking us on a journey from the very simple primes to the foothills of the Riemann hypothesis. In the previous videos we looked at some very simple properties of primes. We looked at what they were, we thought about the question of how many there are. There's an infinite number, we proved it. We also looked at an interesting property of primes, which is that any whole number can be broken down into a unique set of prime factors, and that's quite an important thing. It's called the fundamental theorem of arithmetic. Another almost basic question around primes is to ask, well, how many are there? In the sense of how common are they? How frequently do they occur? Are they dense? Are they sparse? Are they very well spaced out? And there's several ways of attacking that question. One of the ways is to ask, well, what's the average number of primes, or the number of primes up to a given number? And we're going to come back to that. We're going to take a slightly different path today because it's interesting, and also because it kind of follows what mathematicians have done historically. So we're going to think about sequences of numbers in terms of summing their inverses. Now, why is that? Let me draw a picture to help explain why we might do that. So if I've got a series of numbers, I don't know, say A, B, C, D, E, and so on. And these are whole numbers. Now, clearly adding them will give us a larger and larger result. If we take the inverse of each of these elements, each of these terms will be less than 1. So we might have a chance that these things, when added together, either go to infinity or they go to some constant value that's finite, that isn't infinity. Now, how would that happen? Well, if these things don't get small enough, quick enough, then there's a chance that the sum goes towards infinity. If these things get small quickly enough, then there's a chance that actually the sum converges to a finite value. That's the core idea. So depending on whether we end up with a convergence to a divergence or a convergence, will tell us in some sense how far apart A, B, C, D, E are. Let's look at some specific examples there. So the very simplest sequence of numbers that we can think of is just the ordinary counting numbers: 1, 2, 3, 4, 5. And if we ask, well, how frequently do they occur? How far apart are they? And the answer is the simplest one. They're 1 apart. They occur every 1. It's how they're defined. Now, the sum of their inverses is called the Harmonic Series. You might have heard that phrase before. So 1 over 1 plus 1 over 2 plus 1 over 3. Now, you may or may not know that even though each of those terms is getting smaller, the series actually diverges. If we carried on, the numbers would get bigger and bigger, and in the limit, if we had an infinite number of terms, that sum would head towards infinity. That's because, despite appearances, those terms, half, third, quarter, fifth, don't get small enough quick enough. Now, we'll prove this result in a separate short video, almost like an appendix, as it were, because we don't want to kind of distract ourselves in this video. But do have a look at that video, because it's quite a nice proof. So if this diverges, we can in a sense say the sequence 1, 2, 3, 4 isn't sparse enough to cause the sum to converge. So let's look at another sequence where the numbers are actually further apart. So not spaced one apart, but further apart. And these are the square numbers. So these are 1 squared, 2 squared, 3 squared, 4 squared, and so on. Now, if we look at the sum of the inverses, so it's 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on. This is a very famous problem called the Basel problem, and it wasn't solved for a long time. It was a celebrated problem, and it was almost a test of kind of mathematical ability. And a famous mathematician, Euler, did actually solve it when he was still quite young, and that's how he made his name. And the answer is that it converges to a finite value, pi squared over 6. And now again, in a separate short video, we'll go through how that is and show Euler's approach. There are several proofs of that, and Euler's one is quite interesting, so we'll look at that separately. But for this video, the core message is these numbers are further apart than just the counting numbers, and they are so far apart and they spread out, thin out quick enough that the sum of the inverses does actually converge. So that's rather interesting. So the interpretation is that the squares are so spread out, they thin out so quickly that actually when we add the terms in the sequence, we avoid divergence. So let's summarize what we've just said. We've said the sum of the normal inverses tends to infinity, diverges. That tells us that the normal numbers, counting numbers, aren't sufficiently spread out. The next result tells us that the squared numbers 1, 4, 9, 16, 25 and so on thin out so quickly that the sum of their inverses avoids divergence, actually converges. In fact, it converges to pi squared over 6, but that isn't actually important. The fact that it does converge is important. So what about the sum of the inverse primes? Are they so spread out that the sum converges to a finite value like the squares? Or are they not so spread out that actually the sum diverges to infinity? Now that's the interesting question. And the intuition tells us that primes are kind of rare, that, you know, multiples of 2 aren't prime, multiples of 3 aren't prime, multiples of 4 aren't prime, so they kind of should thin out. And we've been surprised before because that path of logic might have suggested that there were not an infinite number of primes, but there were. So let's see where this takes us. So we're going to go through a proof, and I've tried to find a relatively simple proof that doesn't require too much kind of pre-knowledge in terms of maths. So hopefully everyone can follow this. It takes a few steps, so we'll take it slowly and we'll draw kind of a map or a picture of what we've done at the end. But again, it's a proof by contradiction, and we've said in previous videos they're quite common in number theory. They seem to be quite effective. So this is another proof by contradiction. So we're going to start off with the assumption that the infinite series of prime reciprocals, we're going to assume it does converge. Now, if that's wrong, we'll end up with a contradiction. That's how proof by contradiction works. So let's carry on. Now, because we've said by assumption that that sum here, this one here, does converge, it means it's finite, it's a number. Could be 10, could be 100, could be pi squared over something. It's something, but it's finite. So because it's finite and the terms progressively get smaller, there must be a starting point for that sum. So not starting from 1 here, the first prime, but starting from the k plus 1th prime. There must be a k where the sum is less than 1. Now that isn't always intuitive to understand, so I'll draw a picture. So what we've said is S equals the sum of all the primes from 1 to infinity of 1 over Pn, that's the nth prime. If that's a finite value, I can draw a picture of it. And because, and so on. So that's 1 over the first P1, 1 over P2, 1 over P3, and so on. If the sum of these is some constant like 10 or 100 or something, we call it S. Because it's finite and they're getting smaller, we should be able to cut off a point where that sum is less than 1. We should be able to do that. That makes sense, doesn't it? And that might happen at the sum from k equals, I don't know, 10 or 100 or somewhere. We don't know, but it's got to exist because the whole sum is finite and these things are getting progressively smaller, so there must be a cutoff point where the sum beyond that point is 1, less than 1. That's what we're saying here, and we can call that x. So that sum, if we started at the k plus 1th prime, is going to be x, and that's less than 1. We can construct that. Now because x is less than 1, if we construct a geometric series out of it like this, x plus x squared plus x cubed and so on, we know from simple school maths that this thing converges because the convergence criteria for a geometric series is that the ratio between the terms is less than 1. So we've constructed this as well by design. Okay, great. We're just building up some preparatory building blocks. We've built x and we've built g. Now the interesting thing to note about g is that each of these terms, these things, each x, remember, was made of the sum of primes, but those primes were the k plus 1th prime and larger, not smaller. So the terms in this, if we expanded this out, will be of the form 1 over n, where n has prime factors pk plus 1 or larger, not smaller. By construction they weren't in there, we excluded them. Okay, we're still preparing this kind of proof, this attack. We're building these things. So we've built x, we've built g, and we've noted a property of g that its terms don't have prime factors smaller than pk or smaller. Now let's create a different series which is the opposite. Now this page looks a bit scary, so we'll go slowly. It's actually very similar to what we've just done. We're just making another series but doing the opposite. Instead of these terms which have prime factors pk plus 1 or larger, we're making a series where the terms have prime factors pk or smaller. So these primes go from 1 to k and not any larger. And if we look at this kind of denominator here, if we look more closely at it, we notice that because it's 1 plus those primes multiplied by some number, there aren't any prime factors in the range P1 to Pk because they don't divide that 1. We saw this similar construct earlier in a previous video where we said P1, P2, P3 multiplied together plus 1 doesn't have any factors amongst those same primes. It's by construction that we do that. It's a little thing that we've made. So this thing can only have prime factors that are pk plus 1, k plus 1 or larger. It can't have a prime factor of p1 or p2 or p5 or anything up to and including pk. Great. So we've seen this work before, this method, so if you're not sure about that, do refer to a previous video. So if the terms are 1 over something which has only prime factors pk1 or pk plus 1 or larger, it means that f is actually a subseries of g. Let's look at that again. This thing where the n has prime factors pk plus 1 or larger, not pk or smaller. So this must be a subseries of g. So that's interesting. That's something that we can latch onto now. And our proof method is to look at this f that we've constructed here, which is a subseries of g, and ask, does it diverge? And we can use a mathematical technique called a comparison test, a limit comparison test, where we compare it with another series that we know about. And if the comparison of, if we do a ratio of the terms as the terms go to infinity, if the ratio is finite, they either both converge or both diverge. That's the limit comparison test. It's a simple test that sometimes you'll study at school. If not, it's, you can look online. It's not a difficult test. It's quite commonly used in kind of schools, so hopefully you are familiar with it. So what it means is we can test if f diverges by comparing it with, say, the harmonic series, which we know does diverge. So we want to see, does it diverge? That's the question. And if we compare it to the harmonic series, which we know does diverge, we might be able to get an answer to the question. And the way we do it is we take the terms, say term, the f term, fn, and we compare it with, say, hn. We take the ratio, the harmonic series, and we do a ratio. If that's finite, then they both have the same property of divergence or convergence. Now we know h, the harmonic series, diverges, so if this ratio is a constant, then we know that f diverges. The harmonic series is of the form, say, 1 over n or 1 over j, divided by this one, which we've said is 1 over 1 plus j, p1, p2, p3 up to pk. That's a division, so we can bring this to the top like this, 1 plus j times those primes divided by j. Now as j goes to infinity, this thing goes to the constant p1 times p2 times p3 times up to pk, because these j's cancel out and that becomes 1 over j, which goes to 0. So because this limit is finite, we can say that it has the same property as the harmonic series. So harmonic series diverges, so does f. Now if f diverges, and we've said it's a subseries of g, then g must also diverge. Let's look at that statement a little bit more. If if we've got two series, and if one is actually a subseries of another, like that, that is, this has terms, this f has terms in this one, g, but g has extra terms potentially that are not in f. So g is somehow bigger than f because it has more terms. If they're all positive terms and we're adding, then we know strictly that g is more than f. Now if f converges to some constant, we don't know whether g does or not. This might have enough other terms to make it diverge. However, if this one does diverge, then we know that that one diverges as well. That's the intuitive explanation for what we've just said. So g is always bigger than f, and if f does diverge, then of course g does as well because it's bigger. So if f diverges, it's a subseries of g, then g also diverges. But at the start we constructed g to converge, remember? Let's have a look. We built g out of as a geometric series based on x, and we constructed x to be less than 1. So we've reached a contradiction. So that must mean that our initial assumption that the sum of the inverse primes was finite is wrong. So we've shown, in a kind of roundabout way, that the sum of inverse primes diverges to infinity. Now that is interesting, because what it might be surprising, I guess, because what it's saying is that although the primes do get larger and larger and do spread out, they don't spread out sufficiently fast enough for that inverse prime sum to converge, like say the square numbers. So they don't seem to thin out as fast as the squares, for example. That's interesting and I guess surprising as well. So yes, they perhaps become rarer, but not rare enough compared to the square numbers such that the sum of inverses, it doesn't converge. Now we could stop there, but actually there's an interesting famous conjecture, Legendres conjecture, which says that, well, it kind of comes from the same idea that if the inverse squares does converge, the Basel problem, that suggests that the primes are not as sparse as the squares, which might mean that, and Legendre said this, or it is attributed to him that he said this, the history is a little bit murky, that there must be at least one prime between two consecutive squares, because it's saying that the primes are not as sparse as the squares. So in some sense, perhaps on average, but the conjecture says that between any two consecutive squares there must be a prime, at least one. And actually that's unproven today. It's a very simple problem to state, but we don't yet have the mathematical kind of insight to prove it properly. So if you're able to do that, you'll be famous. But it's interesting that this connection between what we've just done and Legendre's conjecture. Fantastic. So actually let's draw a picture of our proof, because it was slightly roundabouty, and it can help to kind of draw a visual map of what we did. So we started with the assumption that the sum over inverse primes was finite. That's what we assumed. We don't know if it's true or not. We wanted to test it. and we wanted to follow a proof by contradiction. What we did is we said that if this is a finite sum and the terms get smaller and smaller, we must be able to pick a threshold after which the partial sum is less than 1. Because the whole thing is S and they get smaller and smaller, we must be able to pick a certain k where the k plus 1th term and so on after that gives us a sum of less than 1. We call that sum x. So an x is less than 1, which means that we can construct a series G, a geometric series, x plus x squared plus x cubed and so on. And we know that this converges because from basic school maths, if the ratio between the terms of a geometric sum is less than 1, then it converges. So we've constructed that by design. We've constructed x by design to be less than 1. We constructed this G to converge because the ratio is less than 1. We then noted that all these terms, if we expand them out, will be of the form 1 over n, where n has factors pk plus 1 or larger, because it can't have smaller primes in it, because we constructed x to only contain those larger primes. We then separately said let's do the opposite, similar to G, but we create another series where the terms are 1 plus, say, sum over j, where they are combinations of the primes from 1 to k. That means that this term here doesn't have any factors that are p1 or p2 or p3 up to pk. All of the factors are in fact pk plus 1 or larger. That means it is f is a, by comparing those terms, it's a subseries of G. F is a subseries of G. So that's a useful connection to have. Now we wanted to ask, does f diverge or converge? And we used a comparison test called a limit comparison test to compare with a harmonic series, 1 over 1, 1 over 2, 1 over 3 and so on, which we know diverges. The comparison of terms as they tend to infinity we showed was finite. So they have the same property. They either both converge or they both diverge. H, the harmonic series, diverges. That means f diverges. But we said that f is a subseries of G. So if f diverges, so must G. And that's a contradiction because we constructed G to not diverge but to converge to some constant. So that we arrived at a contradiction, and therefore the starting assumption that the sum over the prime reciprocals, we assumed it was finite, that it converged, and we were wrong. That's the map of what we've done. We've sort of gone down one path to construct a series G, constructed another one, and we found a way to compare them to highlight a contradiction. Fantastic. Well, I hope that kind of picture has helped you understand from a higher helicopter view of what the proof is doing. So I hope that's been useful. We'll see you next time. Bye.